Next, we got to look at characteristics from a graph. This should be like ingrained in you already, so I'm going to go over this really quickly. But there's some distinctions. Look at this. Look. I'm talking about f here. I'm talking about f prime here, and I'm talking about the second derivative here. So that's very important to make that distinction. For f, if you have positive or negative, or I should have maybe included 0, but if you have positive, that means f is above the x-axis, meaning the original graph is above the x-axis. And then vice versa, if you have f of x less than 0, then the original graph is below the x-axis. Now when we talk about the derivative, that's talking about increasing or decreasing. So, and like notice this distinction, this was what I was talking about earlier. F prime, if f prime is negative, if it's below 0, then f is decreasing. You don't say f prime is decreasing. If you said f prime is decreasing, you're actually talking about the second derivative. So, be very careful with that. And then f prime, if you have it greater than 0, then regular f is increasing. F prime equal to 0, then f has a slope of 0. Not the derivative, but the original function f has a slope of 0. When the second derivative is, and I made the distinction again, the second derivative, when the second derivative is positive, f is concave up. A lot of people, when they're writing out their answers to like a free response, they say, since the second derivative is positive, they say it. They say the word it, and it bugs me. It is concave up. What is it? You have to specify, because you are talking about the second derivative. So if you say it means you're talking about the second derivative. So make sure you specify. If f double prime is positive, then f is concave up. If f double prime is negative, if the second derivative is negative, then f, I can't specify this enough. So if the second derivative is negative, regular f is concave down. If the second derivative is equal to 0, then there's a possible point of inflection. Not always a point of inflection, but possibly a point of inflection. So that brings us to how to get points of inflection. That's what a point of inflection looks like. It's when concavity changes. So you do a sign chart with f double prime. So you want to see when the sign of the second derivative changes from positive to negative or negative to positive. Now also, something worth mentioning is that you can't have a point of inflection on an asymptote. Even though the concavity could change, like if you have something like this and you have an asymptote, you have it concave up, and then you have concave down. There's no point on the asymptote, so there cannot be a point of inflection. So it has to be, the function has to be defined at whatever point you're talking about for there to be a point of inflection. So even though concavity changes, there's no point of inflection here because there's no point on the graph. That's undefined there. So use a chart, sign chart with f double prime. Great. We're moving on. Hopefully this all makes sense to you and you have it stuck in your brain. Again, this one, if you want to find a point of inflection, you take the first derivative, and then you take the second derivative. You set the second derivative equal to 0 to find critical points, and you make a sign chart. And you see when the second derivative changes sign. And if it does change sign, and the critical point is a part of the domain of the function, meaning the function is defined there, then you have a point of inflection. If not, you don't. Remember, critical points also include points where it's not differentiable. So it's like, okay, critical points are where the derivative equals 0 or where the derivative is undefined. Hopefully this is all making sense and you're like, oh yeah, that's a good point. Oh, okay. Even functions and odd functions, we had a free response at the beginning of the year that utilized this fact, and a lot of people were like uncomfortable with it or didn't know it. So even functions are symmetrical about the y-axis. So it, like, you could fold it over the y-axis and it would lay right on top of each other. Then the property, the algebraic property that you can use is this. Maybe I should put that in a box. If you plug in, and hopefully this makes sense, if you plug in x or negative x, you get the same y value. It's like f of x, that's the same as the y, right? So it's saying if you plug in, let's do it for this. If you plug in x, you get this y value, which is what, like -5 or something. Well, if you plug in the negative version of x, you still get -5. You still get the same y value. That's what that means. Now, odd functions are ones that are symmetric about the origin. So if you rotated it 180 degrees, if you were like, that was more than 180 degrees. But if you rotate it 180 degrees, 180 degrees, it ends up as the same function. That's what that means. And the algebraic property for odd functions is right there, meaning if you plug in a -x, you get the same y value except for a different sign. So let's see what that means. If I plugged in 1, maybe I get 1, if this was like x cubed. If I plug in 1, I get 1. Okay, if I plug in -1, I get 1, but negative. That's what this is saying. If you plug in a -x, you get some y value. It's the same as the y value you get from plugging a positive x, except for there's a negative on the outside of it. And the two like big ones are cosine. That's an even function, symmetric about the y-axis, and sine is symmetric about the x-axis. And there you go. That's well, yeah, that's it. Cool. Oh, asymptotes. We talked about this when we did the limits, but I'll mention it again. Vertical asymptotes occur when the denominator is 0 and nothing cancels out, doesn't cancel out. So like terms in the top and bottom don't cancel out. If they do cancel out, you don't have an asymptote, you have a hole. So let's be very careful there. To find these x values for where you have vertical asymptotes, then you set the denominator equal to 0 and you solve. Horizontal asymptotes occur when the limits as x approaches positive or negative infinity. If that equals some number that's finite, then you have a horizontal asymptote. If this equals infinity or negative infinity, you don't have an asymptote. It just grows or decreases without bound. And you take the limits as the x values approach both infinities to find the horizontal asymptotes. And there you have it, children. We got that's the regular like characteristics of a graph. Now we're gonna look at like vectors and polar stuff. Okay? Okay.